So in this video, we're going to describe some characteristics of functions. Not all functions have these characteristics, but these are certain sort of things to look for. We'll just point them out. The first thing I wanted to discuss was even and odd functions. So the name for these, even and odd, this is just a question of symmetry, right? And of course it comes from our friends, the monomials. So if I look at something like x squared or x to the fourth, anyway, x with 2n, so an even power is going to be something like this, right? What we'll see, actually I'm just going to call it f of x instead of 1. Okay? What we'll see is because the power is even, right? If I do f of negative x, it's going to be the same number as f of x, right? So regardless of if it's x squared, x to the fourth, x to the 10, right? It's going to kill the negative. So what you see visually is that this is symmetric around the y-axis. You're just plopping it over. So it's called even when it has this kind of symmetry, basically because these functions have even powers. So let me fix this. So even functions, this is our example, and this is our rule for checking if a function is even. Now this has to be true for every x in the domain, not just some, obviously. So that's it even, and then of course you imagine exactly for an odd function, you can think as an example of something with an odd power. So like x cubed, x5, even x, but I'm going to write it as 2n plus 1. So we know that this is odd, whereas here we're looking at something that has an even power, okay? And it's going to look something like this. What you see here is symmetry around the origin. In other words, this guy just flops over, this guy flops over and down. Okay? And if I want to look at similarly what this looks like, the negative comes out, right? Because it's like x cubed. So f of negative x is negative f of x. Okay? So that's even and odd functions. Now most functions do not have these symmetry properties. Most functions are neither even nor odd. Okay, but that's just how it is. This is just a special property, and sometimes when a function does have a special property, at some point you might find it easy to use that special property. Of course, we know other functions that are even and odd besides our monomials. Sine and cosine are other great examples of functions if I look at cosine of x, it's actually even, right? Because it's going to look like this. Let's just do it like this here. Put plenty of periods in there when deciding what I'm doing. Whereas our sine function is odd, right? Because it's going to do this, right? It's going to do this, and it's going to do this. Try to make it pretty, but you can see if I look at this, this one is just flopping over, and this one is flopping over and down, and sorry, mental thing. By the end of Calc 2, we'll see an interesting reason how these are kind of related to the other ones, but we're still in Calc 1, so we won't go there. Okay, so if you want to prove that a function is even or odd, what you have to do is you have to show one of these two things for every x in the domain. Let's even on. Next thing I want to discuss was increasing and decreasing. And this is exactly what you think that it's going to be. So a function is increasing when the numbers are going up, and it's decreasing when the numbers are going down. So let's call this A, and then something, whatever. So we can say this is increasing for x less than A, and decreasing for x greater than A. Now what's happening at A, it's technically both increasing and decreasing, which is the same, but we're not going to really worry about that right now. All we really need to think about is what's going on with that. Now we can also write down, like we had down here for even and odd, we can write down a definition for increasing and decreasing. So, and I want to point out that when we're talking about increasing and decreasing, we're talking about increasing and decreasing on an interval. So f of x is increasing on some interval I. All right, well, I don't know what I called this A, so we'll just call it CD, right? If for all x1 and x2 in the interval I, so this is the in sign, right? I'll just write it in for now and go over that later. We have that if x1 is less than x2, then f of x1 is less than f of x2. So in our picture, we can imagine this being x1 and this being x2, and we can see that over here, f of x1 is less than f of x2. We're just going to leave it there, and the for decreasing is the same. We're going to leave it there. We're not going to fuss about it too much. You can talk about strictly increasing, which is actually what I wrote here, or just increasing, which allows an equals. So typically when we talk about increasing, we allow equals. We talk about strictly increasing, we don't have the equals. But for our case, we just really want to think about it in a more relaxed sense. Functions going up, functions going down. So again, if I want to talk about my definition for decreasing, it's going to look exactly the same. It's just that if I write the definition for decreasing, let me just write it here. So x2 in I. You still have x1 being less than x2, but f of x1 is greater than or equal to f of x2. The important thing for both of these definitions is that it's on that same interval. So if I'm increasing up to here and decreasing down to there, okay, if I can't compare here and here and here and here, right? Because I'm not going to have this kind of relationship on the whole interval. But if I take this interval, you can see it's increasing all the way. All right, one last thing. Horizontal and vertical asymptotes. So these I know you all know, and we have seen those on many graphs, right? So starting, let me just take something, f of x plus 2 over x minus 3. All right, so this is all, again, review. you know that this is going to have a problem at x equals 3. It's not in the domain. We're dividing by 0, right? So that's going to give me a vertical asymptote here. And now, what's going to happen with this function as we go out to infinity? So we're looking at very large values of x, very positive or very negative. Well, the 2 and the 3 aren't going to matter, right? You're going to end up with sort of x and x. So your long-time behavior of this function actually is going to go towards 1, right? And then what else do I have? If I take x equals 0, I have negative 2/3. I put this here, right? I can plot a few points if I want to know what's going on. What happens if I put in 4? I get 6. Yeah, so something here. But essentially, we can say, without doing too much work, I mean, we can find this point, but bother right now. This is a fairly simple rational function. It's going to look something like this. But I just wanted to remind you, so your vertical asymptote and there may be more than one, are going to happen where you have a denominator of 0 and numerator is not 0. Right? Because 0 over 0, we don't know what that is. So that's going to give you the question here. That's vertical asymptote. And your horizontal asymptote, you can just think about as being the long-time behavior. Long or big, large. It's probably a long time, but we're using x, right? So x, not a time, but if x is a time. So large x behavior. So x getting very large and positive, or x getting very large and negative. And one nice thing about calculus is that when you saw this kind of stuff in pre-calc, it was very hand-wavy. Oh, we're getting very big, we're doing this, these are the rules you have to remember. In calculus, we're going to make this more precise so that you can actually figure this out for more interesting functions than just this kind of sort of straight rational function. And remember some stupid rules. We're going to talk about horizontal asymptotes within the second week or 2-3 weeks, and really get this, make this understandable, because I feel that what you learn in like pre-calc and stuff, it's very fuzzy. It's like, oh, function gets big, function gets small, whatever. Yeah, that's not what we're going to do. We're going to learn a little bit better what's going on there.